What could be so simple and serene as a hand-sewing needle? Yet this serenity belies the art and mystery which lies below the surface of each and every one. This is what we are about to learn. In 1656, the Worshipful Company of Needlemakers was first incorporated to protect the art and mystery of sewing needle manufacture. This was confirmed by Royal Charter in 1664, at a time when the critical skill was to make sufficiently smooth but rigid needles from essentially very rough and malleable wire. The handcrafting of needles lasted until late into the Industrial Revolution, when power-assisted manufacture was developed and when ways were found to create improved rigidity in the finished product. This eventually led to the technology of modern needlemaking. We do not know how Adam and Eve made their needles, but we do know that ancient civilizations used bone, and we do know that the Romans used needles formed from bronze. The earliest industrial evidence available to us are woodcuts from around 1750. Some 100 years after our Royal Charter. These come from the Encyclopedia of Trades compiled by Diderot and D'Alembert between 1751 and 1772. Here we see the sequence of manufacturing operations in needlemaking from iron and also the primitive manual methods employed. Cutting the wire. Stems are cut to the required length from wrought iron wire, which has to be malleable for ease of working. Flattering or flattening the needle head. This is the end where the eye will be formed. Piercing the eye, puncturing the flat head to make the eye. Cleaning the eye. This includes making the gutter for the thread and filing away any flash. Pointing the needle, filing the point, one needle at a time. Hardening the needles. This included adding some form of carbon to form a hard crust on the surface of the wire. Tempering the needles. This is the second stage of heat treatment to create the all-important longitudinal strength. Making up for scouring. Wrapping up the needles in rolls with emery powder and fish oil. Polishing. Rolling the needles against each other back and forth in the rolls under a lead weight. This can take up to 2 days, involving changes of linen wrapping and grade of emery powder. Drying. The needles are then washed in warm soapy water before being dried in a rotating barrel with warm sawdust. Manufacturing was not in fact conducted in a large factory or in such idealistic surroundings as the woodcut implies. Needlemaking remained essentially a cottage industry until the start of the 19th century, when processes were gathered together in manufactories. Most of the same manual processes persisted, as you will see from this old Needle Industries film. Cottage needlemakers hammered out their own needle stems from wrought iron, but early on in the Industrial Revolution, the ability to draw wire proved to be a great advantage, as this saved a great deal of forging time and effort. The gauge of the wire determines the size of the needle. Pieces of wire cut to the required needle length had to be straightened by rolling on a wooden block. The next stage is to flatten one end of the wire on a steel anvil in order to make an eye. After this, the position of the eye has to be marked using a suitable punch. The position is marked on both sides of the flat. And finally, the eye is punched out on a lead anvil. It is also punched from both sides. Whilst the eye is still impaled on the punch, the sides are hammered up to form a gutter down which the thread can pass. The eye and thread path have then to be cleaned out on a wood block, using a guttering iron. Afterwards, it is given a final clean-up. To complete the needle, the wire has to be pointed at the other end using a suitable file against a wooden block. And this is the finished needle. As the demand for needles grew, methods had to be found to increase production. By around 1900, coils of wire of the desired gauge could be drawn by the larger needlemakers themselves, or purchased from wire drawers. The first operation was to cut stems to the required length using foot-operated shears. Because they had been cut from the coil, the stems were curved and had to be straightened. The stems or wires are arranged in rubbing rings, after which they are put into the furnace and heated to redness. When hot, they are brought to an iron bench and rubbed for around 20 minutes using a rubbing iron. This action moves the wires round within the rings and straightens them. And these are the straightened wires. It is worth seeing this sequence over again, but without lights and under the conditions which actually existed in one of the old hardening holes in the Redditch area. Here once again are the straightened wires which are ready for pointing. Pointing was a very dirty and dangerous process due to the threat of shattering grindstones and absence of dust extraction. Pointers died at a very early age from pointer's lung or silicosis. Even when extractor fans became available, pointers would not initially use them because of a drop in wages through the withdrawal of their danger money. Here is the process of hand pointing with dust extraction. The wires are rolled by hand against a flat grindstone. Here are the pointed stems with the points at both ends. Next, the wires have to be flattened and eyed in the middle to make two needles. At first, this was achieved with hand tools such as these. Here, the wires are being flattened by this punch and die to make two eyes in the center. Two tools which greatly speeded up the process were the kick press for stamping and the fly press for eyeing. The kick press has two dies, one in the bed and the other in the hammer. These flatten the wires and also mark the position of the eyes ready to be punched out. Here are the flats and the dies which made them. The fly press now comes into action to punch out the eyes, the position for which has already been marked during the kick press operation. These are the pairs of pointed and eyed needles which have to have the burr ground from around their eyes. The next task is to spit the double-eyed stems, threading wires through the eyes so that several can be ground at the same time. These spitted needles are now ready for the burr grinder. The burr is carefully ground off from both sides of the eye until a very smooth finish is achieved. Once they have been ground along the sides, the pairs of needles are broken apart so that the ends can be ground round the eyes. They are clamped as before, levelled up, and the ends ground round. Here once again is the action of cleaning the head. And lastly, a final smoothing. At this time, many items produced this way were destined to be surgical needles and so had to be curved. The curve had to be hand-formed round a mandrel before the needles went to be hardened and tempered. The needle-making sequences shown so far have had to use malleable iron wire to make the stamping and filing processes feasible. This unfortunately results in sewing needles which are rough on the surface, chunky, and bendy. All these features are unsuitable for modern usage. Although the physical properties of wire were not fully understood at the time, the necessary rigidity in needles was progressively sought by the processes of hardening and tempering. Hardening and tempering was not new for large items of iron, but was being adopted for multiple small items like nails, pins, and needles as early as the 17th century. This led to the needlemakers of London obtaining an edict from King Charles II, banning the import of unhardened and hence cheaper needles from the continent. The sequence of the hardening processes up to the early 20th century was as follows. Before the development of carbon steel wire, the needles had to absorb carbon in a process called pieing. The needles were put into a cast iron pot, together with carbon in the form of charcoal, carbon black, or even crushed bones. The lid was then put on the pot and the whole heated in the furnace. The surface of the wire would absorb carbon and, after cooling slowly, would become suitable for hardening. The hardening process entailed loading the needles onto cast iron trays and heating them in a furnace to the correct intensity of redness, notionally 800 degrees centigrade, and then quenching them in whale oil or cod oil. At this stage, the needles become brittle like biscuit and certainly not fit for their intended end use. After multiple washing to remove the oil, the hardened needles are laid out on a tray for tempering. They are heated to around 200 degrees centigrade before being allowed to cool slowly. This creates strength and rigidity in the needles. The manufacture of the needles is now complete, and the needles are ready for scouring and finishing. The difficulties with the processes we have seen are that they are very imprecise and are not controlled to the accuracy which is needed for a reliable hard case over each and every needle. To illustrate how rudimentary the hardening process was, here is a different method used by one hardening hole in the West Midlands. Here, the tray of needles is loaded directly into the fire. When deemed hot enough, the needles are again quenched in oil. The fire is then stoked up with coke, and the needles are taken out of the oil, laid out on trays, and loaded again into the fire. This time, the oil is burnt off. The tempered needles, still flaming, are placed outside to cool. They certainly need to be cleaned and scoured after this treatment. The addition of carbon to the surface by pieing was patchy, as it depended on direct contact with the needles, so there were variations in uptake from one needle to another and within the same needle. The basic fabrication of the needle was now complete, but what remained was to ensure that the individual needle was clean, with a smooth surface for sewing and as rust-resistant as possible. All these elements were addressed by the sequence of processes called finishing. Up to the 1930s, this sequence started with the process of scouring using emery powder, soft soap, sawdust, and human or mechanical elbow grease in a repeating sequence lasting up to 1 week. At this time, needles were placed in linen and canvas wrappers, then emery powder and soft soap added. The canvas wrappers were then tied tightly in rolls, soap suds added, and the packages were rubbed to and fro under weighty rubbing sets for 8 hours. The needles were then hand-washed in a bowl using soap suds. Depending on the finish required, this process could be repeated several times with progressively finer grades of emery powder and new wrappers. Remember, 1 day per process. This achieved the smoothness of surface, but rust prevention entailed 1 or 2 further runs with new wrappers and a mixture of olive oil and tin oxide for a final glazing of the needles. The final drying was achieved by tumbling the polished needles in heated sawdust. The separation of the needles from the sawdust was the final back-breaking process of winnowing by hand. The breakthrough came with the advent of specialist wire manufacturers, who were able to produce mild steel or carbon steel wire with a predetermined percentage of carbon uniformly throughout the wire, and not just on the surface. From the latter part of the 19th century, the energies of steam and then electricity were key to the development of wire drawing machines. This made it possible to produce wire to a much smaller gauge, and this enabled the production of much finer needles. The new wire also allowed new high-speed production with many fewer operations. Wire straightening and cutting the stems to the length of 2 needles. High-speed pointing of both ends of the stem. High-speed needle stamping, then eyeing, then removal of burrs at 2 needles a time on a machine imaginatively called a combine. All this was made possible by the production of stamps and dies from hard steel made by the same hardening and tempering principles as for needles. Hand pointing is still retained for blade points for leather work and for triangular points for canvas work. Temperature control and uniform exposure of needles to heat gave greater speed and reliability to hardening and then tempering, with final washing in vibrators taking a fraction of the traditional human input and processing time. Modern manufacture benefits from the higher and consistent quality of the drawn wire and from the development of plating. In the early days of plating, scouring was in vibrators, and plating took place in standing baths with the needles being stirred by hand to achieve a uniform covering of nickel. A single flash application of nickel gives rust-proof needles and friction-free sewing for fine fabrics. The most recent developments in plating see the needles being loaded into double-lined plastic barrels, which can be closed and then rotated. The rotating barrels are then transported manually or automatically in and out of a line of standing baths for cleaning and scouring, before the plating itself, and then final washing. The plated needles are then tipped into heated centrifuges for drying. Nowadays, plating is the standard finish for hand sewing needles, but surgical needles have to be nickel-free because of allergy in some patients, and so stainless steel is used. This is a much harder wire, more difficult to work, and it wears the tools comparatively quickly. The whole manufacturing process is much more expensive, so stainless steel is limited to medical usage. The head of today's surgical needles is radically different, as the suture thread is clamped into a channel at the top of the needle rather than being threaded through the eye. This preserves an even diameter between needle and thread and so helps wound repair. The availability of a wide range of wire gauges and improved processing have allowed considerable specialization in needle assortment. Hand sewing needles now offer a wide range of sizes, gauges, and point profile for different fabrics. Specialist needles are made with scalpel-shaped points for both heavy and light leather work. Triangular points are produced for canvas work, and mattress manufacture requires its own range of needles. In the interest of making the fullest use of the developing technologies, any self-respecting needle maker would offer a range of fish hooks. Not to be outshone by competition, one or two needle makers in the Redditch area even went on to manufacture fishing rods. Finally, in the 21st century, old staple products like hat pins or gramophone needles have been replaced by electrical or engineering components. Over many decades, the masters of the Worshipful Company of Needlemakers have used an especially commissioned etui of hand sewing needles as their main calling card, or for presentation on special occasions, including prize winning at sponsored competitions. Nowadays, the needlemakers concentrate on charitable work, which includes promoting the underlying skills of needle manufacture. These are still evolving apace through developments in metallurgy and through computer-based design and computer-controlled manufacture of both high-precision tools and final products. This is achieved primarily in conjunction with the city and guilds apprenticeship schemes, where the latest technology features high in the syllabus. In addition, we seek to support technical development in individual companies. The livery also promotes and supports the use of needles in traditional occupations like sewing or embroidery. In the year of Queen Elizabeth's Jubilee, we were honoured to sponsor and support the tailoring of new bishop's copes at Southwark Cathedral. We continue to donate prizes at annual needlework or quilting fairs. In more recent years, we have established medical bursaries for projects involving the use of needles in conjunction with the Royal College of Surgeons and the Royal College of Nursing. All this is in addition to our long-established support for the Textile Restoration Department of the Victoria and Albert Museum, the Royal School of Needlework at Hampton Court, you can see one of our prize winners, and the National Needle Museum in Redditch. The Worshipful Company of Needlemakers will continue to promote the art and mystery of needlemaking to help offset its recent decline in the United Kingdom, and we look forward to supporting others in their development of new concepts in needles, new prime materials, and new high-tech methods of manufacture. The more we can harness high technology, the less needlemaking will depend on low-cost labour overseas, and the greater the opportunity for reinvigorating the manufacture of needles in the United Kingdom. The needlemakers of London enthusiastically accept the challenge of a changing world. We hope that you will share this enthusiasm with us.